Welcome, everyone. This is Lecture 11 of our Social Network Analysis course. Today, we will explore one of the most influential and fascinating concepts in network science, cascading in social networks. This lecture will guide you through the mechanisms that cause information, behaviors, and content to propagate across social platforms. We will examine decision-based spreading, epidemic-based probabilistic models, and 2 real-world case studies. By the end of this session, you should have a deep understanding of how viral content forms, how it spreads, and how we can model these processes mathematically and computationally. Let's begin. In this lecture, we will cover 2 major sections. First, we will study decision-based cascade models. These models describe spreading as a result of user decision-making processes: exposure, evaluation, choice, action, and propagation. Second, we will introduce probabilistic models derived from epidemiology, the SIR, SIS, and SIRS models. These 2 families of models give us powerful tools for predicting virality, analyzing influence, and understanding network behaviors. This lecture supports course learning outcome number 2, the ability to apply modern intelligent systems in analysis and solution development. More specifically, you will gain the skills to implement social network analysis in a project, to identify influential nodes, detect communities, analyze relationships, and visualize cascading patterns. These skills are essential for data-driven decision-making. To begin, let us define what a cascade is. A cascade is a sequence of events in which one user's action triggers another user's action, which then triggers another and another, forming a chain reaction. On social media platforms, this could take the form of a retweet chain, a meme spreading across communities, a viral challenge, or the rapid propagation of news or misinformation. Cascades are important because they explain how trends form, how influence moves across a network, and why certain pieces of content go viral. This slide references a short video visualization demonstrating cooperative behavior spreading in a circular network. While we won't play the video here, I encourage you to watch it later. It offers a helpful visual intuition. When one person changes behavior, neighbors may follow, and that influence continues outward across the graph. Let's examine the fundamental mechanisms behind spreading. First, the state of a node, whether it has shared the content or not, depends on its own history and on the history of its neighbors. Second, exposure is not constant. It is stochastic and depends on a user's previous interactions, algorithmic decisions, and platform-specific behaviors. Third, multiple entities may spread simultaneously. This means we may observe competing trends, interacting cascades, or situations where one piece of content suppresses another. These principles apply to memes, news, rumors, or even behaviors such as joining a movement or participating in an online challenge. In random networks, the local structure resembles a branching tree. This has an important implication. Whether a cascade survives or dies often depends on the first few spreading attempts. If the initial activated node successfully influences its neighbors, the cascade begins to expand. If it fails early, the cascade ends almost immediately. The key theoretical question is, given a particular network and a contagion process, can global spreading occur from a single seed? This is analogous to asking whether a spark can ignite a large fire. A cascade is a chain reaction. Real examples include meme propagation, hashtag challenges like the Ice Bucket Challenge, viral political messages, and fast-moving trends on platforms such as TikTok, Instagram, and X. Cascades matter for 3 main reasons. They determine reach, they reveal influence, and they shape trends in digital environments. Decision-based models assume that users do not behave randomly. Every interaction, viewing, liking, sharing, or ignoring, is the result of a decision. These decisions are guided by visibility, whether the platform shows the content, perceived value, social proof, such as how many friends shared it, personal preference, identity, and taste. Understanding these factors gives us insight into micro-level motivations behind viral phenomena. At the core of the decision-based model is a simple cycle: exposure, evaluation, decision, action, propagation. This sequence repeats as the content moves from one user to another, expanding the cascade. Exposure occurs when the platform's algorithm displays content to a user. The likelihood of exposure depends on the follower graph, algorithmic ranking rules, and engagement signals such as likes or comments. We quantify this with reach probability, the probability that a user will encounter the content. Next comes evaluation. The user asks internally, is this relevant? Is this valuable? Is it socially acceptable to share? Evaluation depends on the user's interests, their community norms, and the emotional or informational content of the post. High relevance increases the likelihood of sharing. A third step is the decision stage. A user's decision is influenced by utility, the potential benefits of sharing, cost, social backlash, effort, or reputational risk. Social influence, friends or community members who have already shared. Personal norms, internal rules that guide behavior. The decision to share may be motivated, strategic, or instinctive. In this stage, the user chooses one of two actions: share, which triggers the next propagation step, or ignore, which ends the cascade at that node. The simplicity of this binary choice belies its impact on global cascade dynamics. When a user shares, new audiences gain exposure. The cycle repeats, resulting in either exponential or linear growth. We measure spread using the viral coefficient, denoted as R0, R0. If R0 is greater than 1, the content spreads. If it is less than 1, the cascade eventually dies out. We can model share probability mathematically as P of sharing equals a function of utility, cost, visibility, and social proof. This function can be implemented using logistic regression, agent-based simulation, or graph diffusion models. These form the quantitative foundations of cascade prediction. The size of a cascade is shaped by multiple factors. 1. Network structure. Dense networks spread content efficiently. 2. Content quality. Engaging content spreads more easily. 3. Influencers. High centrality users amplify reach. 4. Algorithms. Platform boosts can accelerate spread. 5. Timing. Posting during peak activity increases reach. These factors interact to determine cascade potential. This slide displays a simulated set of cascade size distributions, showing typical power law behavior. A small number of cascades grow extremely large, while the majority remain small. This is a hallmark of social propagation systems. Cascade modeling has widespread real-world applications, predicting whether content will go viral, optimizing content design, identifying key influencers, monitoring crises or misinformation, performing A/B testing for communication strategy. These tools are widely used in marketing, public relations, and policy planning. To summarize, decision-based models explain virality through rational or motivated user choices. Improving exposure and utility increases cascade potential. These insights are highly valuable for marketers, platform designers, and digital strategists. Modern analytics tools incorporate cascade detection, forecasting, user decision modeling, and mapping of influence pathways. These tools rely heavily on probabilistic modeling. We now move from decision-driven models to probabilistic and epidemic-inspired models. Probabilistic models treat content as if it were infectious. A user transitions between states based on probabilities. This allows us to forecast virality, measure contagion, and understand when trends will saturate. Because content spreads like a virus, sharing acts like transmission, ignoring acts like recovery, and users may become susceptible again. These models have decades of scientific validation behind them and map very well to online behavior. We focus on 3 epidemic models: SIR, one-time bursts, SIS, continual cycles, and SIRS, seasonal or periodic spreading. Each model corresponds to a different type of content lifecycle. In the SIR model, users move through 3 states: susceptible, infected, and recovered. This reflects short-lived viral trends that peak quickly and fade. The curve begins with a single infected node, rises sharply as the cascade grows, and then declines as users lose interest. This curve resembles classic epidemiological behavior. In the SIS model, recovery is temporary. Users alternate between susceptible and infected states, and can be reinfected repeatedly. The two parameters remain beta and gamma, but there is no permanent immunity. This enables ongoing conversations and repeated cycles of engagement. SIRS adds a third component, loss of immunity. Users eventually become susceptible again, supporting seasonal or recurring virality. The three parameters are beta for infection, gamma for recovery, and delta for immunity loss. This produces multi-peak cascades, waves of virality occurring over time. In summary, SIR is suitable for one-time spikes, SIS is ideal for continuous engagement, and SIRS is best for seasonal or recurring trends. These models support virality forecasting, trend duration estimation, influencer identification, marketing timing decisions. They bring structure and predictive power to social media analysis. Examples include SIR for viral memes, SIS for political debates, and SIRS for annual event campaigns, such as holiday promotions. To summarize, epidemic models provide powerful insight into the different shapes and life cycles of digital cascades. We now turn to two case studies that illustrate cascade behavior in real-world datasets. This dataset includes over 2 million users, more than 11 million photos, and 34 million favorite interactions across 100 days. It offers a rich environment to study how content spreads. The case study addresses three core questions. Does content spread along social links? What is the timing and structure of dissemination? And can epidemic models explain the observed patterns? Users may discover photos through their home feed, featured displays, external websites, search results, or connections in the social graph. These pathways demonstrate that content may spread socially, algorithmically, or through external mechanisms. To identify whether a bookmark event was socially propagated, we compare the user's action timestamp with the actions of their friends. If at least one friend bookmarked earlier, the event is considered social. Key findings include: social cascades do occur. R0 ranges from 1 to 190. Online networks are extremely efficient transmission media. User behavior is highly heterogeneous. These insights underscore the strength of network structures in enabling virality. The second case investigates the propagation of a global petition chain letter. Researchers identified hundreds of petition copies, cleaned the data, built propagation graphs, and used a maximum weight spanning tree to infer the underlying cascade. Remarkably, the resulting propagation tree was deep and narrow, contrary to expectations of a shallow, wide small world process. This slide lists key readings from Barabasi, Newman, Watts and Strogatz, and Tang and Liu, essential literature for further study in social network analysis. Thank you for your attention. In the next lecture, we will continue exploring advanced concepts in social network analysis.